from Korea University. Actually, I asked Dr. Liu and Dr. Park to host Professor Ying-Jer, who is our speaker today. So I will introduce him myself, although I'm a member of PCS. So, and of course, I sincerely appreciate the PCS for this great hospitality. And yeah, so Professor Kao got his bachelor degree in National Taiwan University and received master and PhD degree in University of Chicago. So after working in Canada as a postdoctoral fellow, he joined National University, Taiwan University as a faculty member in 2005. And now even he is serving as the president of the Physical Society of Taiwan since this year. So he must be very busy now. So he is a very active and well-known expert on the computational many-body physics, especially on the quantum many-body physics. And he has been studying a lot of interesting topics, including the quantum speed liquid or quantum magnetism and exotic phases of matter using the state-of-art numerical tools such as the tensor network, DMRG, and even machine learning recently. So we are going to learn about one of our very interesting recent works, which is about the variational tensor network. So let us welcome him with applause.
And thank you, PCS, for hosting me. And it's a great pleasure to be in Korea again after almost 3 years staying at home. And this is my first international trip in this past 3 years. Okay, so what I'm going to tell you today is something we recently worked together with Hyung-Yong and his group Wei-Ling, and also my students Yu-She and Xu-Ke. And so this can be this title can mean a lot and it can mean nothing to people. So I'm going to explain what I mean, what we're going to do. And if you're interested into the details, you can see the paper is on the archives. Okay. So okay. All right. Okay. Sorry for the technical issues. So before I start, I want to introduce some diagrams because I'm gonna show a lot of these diagrams. So these are the sort of like a language for practitioners of the tensor network algorithms. So here I'm gonna use this symbol. Basically, if I have a one open leg, means that this is a one index object, so it's a vector. And with two legs, it's a matrix and rank 3 tensors. And so then the Einstein summation convention will be just if you ever repeated the index, so basically you link the leg, then it becomes a multiplication, a contraction, and you get a new tensor. So you can apply it to more complicated case. And and the scalar is basically just something that we saw external indices. And the operator is basically, here is a local Ising operator with a sigma z, sigma z. You basically take two states with two index, the side 1, side 2, and maybe to another state with side 1, side 2. So this is the tensor product. Okay, so these are basically the notation we're going to use in the following. Okay, so what is a tensor network, or commonly, or in general, tensor network states? So basically, it's an ansatz inspired by quantum information science to write your as approximation to write your quantum many-body wave function. So in general, I have a quantum many-body wave function, and we know that the Hilbert space of this quantum many-body wave function grows exponentially with the number of sides. Right? So tensor network states are basically just a low-rank approximation of this quantum many-body states. For example, I can try to decompose this high-rank, high-dimensional many-body states into, say, something like this. So this is what they call the matrix flaw state. Each open leg is a physical index. So if you have a local Hilbert space of 2, then it's spin up, spin down, right? But the price you pay is you introduce this so-called virtual indices. So this basically control the entanglement between the two sides. And there's a different way to decompose your quantum many-body wave function. And the idea is that we want to decompose the wave function in a way that this ansatz will satisfy the entanglement area law. So which means that the amount of entanglement between two parts of the wave function depends on only the boundary between these two parts. And so we have a knob to tune this chi. We can tune to control the amount of entanglement included in my ansatz. Okay. So now we treat this as some kind of a quantum variational wave function ansatz. Okay. So the two commonly used tensor network wave functions are in the 1D is called the matrix flaw state. So if you fix the physical bound, it basically just a rank 2 tensor, so it's a matrix. And if you can generalize this higher to higher dimension in 2D, then it's called a PEX, project entangled pairs state. And the entanglement entropy of this ansatz, for example, in MPS, if I cut here, the entanglement between this part at the left-hand side and the right-hand side is always bounded by this bound dimension chi. Okay. And so if I want to say, okay, in the 2D case, I want to cut this part A and part B, and the entanglement is always proportional to the boundary. Okay, so this is by design the ansatz that we want to use. Okay, so the good thing, you may ask, oh, this is probably very restrictive, right? But the good thing is that the typical many-body wave function, at least the ground state, they satisfy this so-called entanglement area law. So these ansatz are good description of quantum many-body wave functions of the local Hamiltonians. And the success stories using the TNS, tensor network states, in solving problems in frustrated mechanisms. For example, the IPAP algorithm has been used extensively to solve the problem of this Shetry-Sutherland compound, sodium copper fluoride. And as you can see, this is a very complicated phase diagram in terms of pressure and field. And a lot of has been resolved using this IPAP algorithm, and it's been confirmed with the experiments. Okay. So this is one of the very powerful tool to study frustrated mechanisms. Another example is this model, this seemingly simple model, this antiferromagnetic Heisenberg model on carbon lattice. And people have been debating for forever what's the true ground state of this model. It's just a Heisenberg interaction between the lattice size and you have this Kagome lattice, similarly very simple. But for a long time, people cannot agree on what is the ground state. And recently, it's been converted to like if the ground state is a Z2 topological spin liquid or it's a Dirac spin liquid. Okay. And the current consensus seems to be suggesting the Z2, that's right, the gapless spin liquid. So we did a study with slightly added preparation to this state. And this state, it turns out that we found by adding the DM interaction, this state will become a symmetry breaking state into a magnetic order state. And the interesting thing is that what we estimated for the critical coupling for this DM interaction is actually much smaller than what's been suggested in this real material Herbert-Smith side. Okay. So, and a quick advertisement. I think recently we revisited this problem. We find maybe there's a suggestion. Maybe this is a Z2 spin liquid. Okay. So I think the saga goes on. But what I mentioned here is what people basically just take the ansatz and then try to optimize it in a very brute force way. So I have a lot of parameters. I try to optimize it and see if I can get a good ground state wave function. But recently, especially people start to think, can we not using this brute force, but we think about is there symmetry or there's some way we can create some ansatz to understand to impose some constraint on this ansatz, and we can also map it to some classical physics that we can understand. And in a pioneer work by Hyung-Yong and Naoki Kawashima's group, they basically realized that all this Kitaev-like model can be mapped into the norm of the wave function can be mapped into a partition function of classical gases. And that make life much easier to understand what's going on with these quantum wave many-body wave functions. And what we did is that we can use some modern technology of these tensor networks to understand what kind of excitation is for line excitations is for this Kitaev model. And we also confirmed Hyung-Yong's prediction that this is a abelian spin liquid, lead to a abelian spin liquid. And we found that the single particle charge excitations are, single particle excitations are basically charge excitation, unlike in the spin 1/2 Kitaev models are fermions. Okay, so these are photon excitations. Okay. So let me summarize. Computationally, what do you want to do when you want to study the tensor network states in using a tensor network state to study frustrating magnets? From the computational aspects, is first you try to obtain a ground state wave function, and there are several methods. There's something called simple update or the imaginary time evolution, which is cheap but it's less accurate. And there are some other methods. What we call the full update, or what I'm going to call is a variational updates. Variational optimization, they're more accurate, but it's very, very expensive. And there's some other way you can borrow the technique from the machine learning community using this automatic differentiation. There are some promises, but there are still some issues that they might encounter. So this is the difficult part, optimizing, getting the ground state. And a lot of things that you maybe want to enforce. For example, you want to enforce some closed conserved quantities, for example, flux. So for example, the Kitaev model, you know that the ground state is an eigenstate of the global flux operators. And how do you enforce those global fluxes? It's actually highly non-trivial. Okay. So after you obtain the ground state wave function and you want to compute some expectation value, and some of the standard methods developed. For one method, it's boundary matrix process, or you can do some common transfer matrix. And the good thing about this is this may also give you some information about this excitation and also other things. Okay. So something is not commonly talked about is how do you have a tensor in a wave function? Can you read more out of this your wave function? And there's a recent development that you can sort of like use something called a virtual order parameter to determine if the tensor you obtain for the ground state is in the topological phases or not. Also, you can get the excitation from the transfer matrix spectrum. So what I'm going to talk about today is the first part actually. Is there some general way to obtain a good ground state wave function? Because we know that this is the first part of understanding a very complicated quantum many-body system. So, as I said, there are two ways. The first way is more complicated, it's very expensive. Basically, you do a variation optimization. You directly optimize all the parameters of the tensor. And basically, here the schematic, it shows that I have a wave function, a trial wave function. I try to compute the expectation value of the say, the Hamiltonian. So in this case, the local Hamiltonian. And I will try to evaluate this, and I adjust my parameters in my wave function such that I lower the energy. Okay. It sounds very simple, but there are a lot of issues because this is a local optimization, but we have to include all these environment tensors, what we call, so basically representing to other part of the wave function that we're not optimizing. Okay, so that's the expensive part. And so the pro of this method is it uses the full tensor network source. Right? But the cons are these are very computational demanding, very expensive. So this is the case is 1D, and he mentioned that you want to do a two-dimensional calculation or three-dimensional calculation or four-dimensional calculation, and this scales up very badly. Another easier way is just keep doing the projection. So this is what we call the imaginary time evolution method. So we know that if I have some trial wave function, as long as this trial wave function has some non-zero overlap between the ground with the true ground state, then I can keep doing this projection. Okay, so here is the imaginary time evolution, imaginary time evolution operator. I just keep projecting using my Hamiltonian, keep projecting it, and assuming there's no degeneracy of the ground state and so on, then I do enough times of this projection, I should get the true ground state. And so in real life, this is not so simple because this is a global operator, and I have to do. All I can do is local operations. So even if you want to do this on a quantum computer, you have to decompose into a local unitary case. So in practice, we have to use this so-called structure to do decomposition. And so we just decompose the global operator into some local two-side operator or some local operators and keep doing this. Okay. So in this case, there's no variational parameters. So it's just keep matrix vector multiplication. So it's very cheap. Right. But the bad thing is that you don't really have a variational principle to protect you, right? And you also suffer from all these truncation errors. And if you want to do a more complicated Hamiltonian, it actually becomes increasingly difficult. So this is like there's two different extremes of the methods. There's somewhere in between, right? We can borrow ideas from both and come up with some. So it's not perfect, but half-half. So that's the idea.
So is it in this case, for this imaginary time management,
Yes.
if there's no variation of parameters, then at the end of the day, you may not go to the
Yeah.
crossing.
Yes. You don't know.
So just keep doing and you expect,
Yeah.
but we don't know the answer.
Yes. And in practice, because we also have to do some truncation, in practice, we sometimes see that this imaginary time evolution will go to, will get the energies much lower than the true constant.
Mhm.
So, yeah. So this is basically how it works. And in practice, this is a lot of, if you read a lot of these tensor network calculations, this is what people use, because the other alternative is impossible. So another question we want to address is, how do you class, you get wave function, right? And how can you use this wave function hidden in the information hidden in the wave function to quantify your quantum phases? And so one thing about this, one good thing about this tensor network representation is that there's something called the gauge redundancy. I'm going to skip the details, but since this is a matrix product, so I can insert identity here, and I just absorb the wave function. So I get a totally different tensor on each side, but it still represents the same wave function. So this gauge redundancy, if you really want to classify the phases or really fix the optimization, causes a lot of problem, because you have a lot of the redundant degrees of freedom, making your optimization very difficult. But people realize that you can use this to classify quantum phases. Okay, so basically, by introducing some ideas of relating to the symmetry in the physical space into the symmetry operation in your virtual space. And this can allow you to check if it's in the symmetry breaking phases or if it's the SPT phases. And also, there's some this virtual symmetries also allows you to check if this tensor represents an intrinsic topological order. Okay. So a lot of these things, especially these topological order phases, used to be that you had to compute a global thing. Then you need to compute the topological entanglement entropy, which is computationally expensive, but now becomes a local thing that you just compute. Okay. So I'm gonna go technical pretty quickly. So
I think having such a relation does not guarantee the topological trivial.
Yes.
So even though the tensor satisfies such a relations, still the resulting state could be trivial. So
yes, there's a lot of bugs you have to check, but for simplicity,
yes.
So this is something that you can do. Okay. So before I go technical, I'm just going to summarize the main results. So there are two things. The one thing is that we propose a systematic way that you can get the benefit of both. And so you can obtain a very good ground state with less parameters, but comparable with this full variational optimization. And the good thing is that in the past, if you want to study say topological order state, you have to constrain your tensors. But here we don't have to constrain our tensors; we just optimize. But surprisingly, by doing this optimization, this symmetry will emerge. Some of this gauge symmetry will emerge. Okay, so how should we motivate this method? This variational tensor network operator. So let's start with something simple. So I'll start with the so-called frustration-free Hamiltonian. And so frustration-free means that each local term annihilates the ground state. Okay, so this is the definition of the frustration-free. So at the ground state, each local term annihilates the ground state. And I'm going to restrict myself even further. I'm going to just use the frustration-free commuting Hamiltonian. So that means that each local term, each local Hamiltonian commutes with each other. If this is the case, my ground state projector, remember this guy, this is my imaginary time evolution operator, then I can write exactly as the product of these local terms. And this product of this local term, I can do an expansion, the power series expansion for each local term. So in this case, this is a very simple case. The projector to my ground state is basically just a tensor product of these powers of these terms, right? So which means that I know how to write this as a tensor network. So I have a tensor network representation of this projector for this very restricted but interesting, right? Hamiltonian frustration-free commuting. Okay, right. So this is actually the inspiration. But let's say, okay, I have a general Hamiltonian. But the general Hamiltonian, I don't have these conditions. Okay. Then I cannot really write in terms of those, right? So I can try to expand my ground state projector, but the price to pay, I have some of these local terms and power. For the previous case, I can just I have the power. If I expand this, I take the power and then sum. But here I take the sum first and then take the power, and these things become very messy. And since also these local terms don't commute, then things are complicated. But so there are terms that I cannot have a simple tensor network representation. But let's pretend they don't exist. Okay, they just pretend they don't exist. Since we say, okay, these are local, so maybe most of the terms are okay. Only when these terms have some overlapping size, these are not okay because then they don't commute. But most of the terms are okay. So let's pretend that they're okay. So we construct something based on the same idea, but for those other terms we try to minimize those effects or try to massage it such that it works. Okay. So the construction the following will be a little bit technical. So to construct this, I restrict myself into a two-side interaction. And for any two-side interaction, I can always write this in terms of a three-lag tensor, and there's a contraction. The good thing about writing in this way is it looks like a vector. I can define this as a vector operation, but these are operators. The reason why they are operators is because they bring a physical state to another physical state. So this is two vectors contraction. So I'm actually contracting in the virtual Hilbert space. Okay. So for any two-side interaction, I can easily do a simple exercise. For the Heisenberg model, I have this. So my L will be something like this, and R will be something like this. And so XFC model, I think this is very easy to verify. But the important thing is I want to take the power of these guys. So this is our basically just this, right? This Hij. But I want to take the power of these guys. And the power of these guys, what would happen? Okay. And so I basically, I should say, okay, I hope that using this as my basis. So all these vectors A and B as a basis, I assume that power of this Hamiltonian can be written as something like this. Okay, so there will be some coefficients and there will be some expansions, right? So, and this can be easily achievable as long as there's a closed condition. So, for example, I can square this, then I get the identity, right? So, which means that although I'm taking the powers, but actually there's a finite terms in the expansion. Okay, so then I can use some properties, and also because remember there are some non-commuting terms that I basically ignore. So we did, we can sort of like let's try to mix these terms in a different way. So I do the symmetrization. So this is and by doing this, if at the end I get a operator. So this is my call, or what I call the generic tensor network operator. So it's coming from this two-side operator, and then you do a symmetrization to represent all those things that you cannot really represent, to sort of like make things more interesting. Okay, so the good thing in this answer, so far I didn't introduce any variational part, right? This is the exact up to now. But as I said, there are some parts I don't want. So I can just sort of like introduce some parameters in front of these block Hamiltonians or the block operators. And those are basically what we call my variational answers. Okay. So a few comments before I go into the real construction. So remember, my Hamiltonian has symmetries. So this P is basically some polynomial of my local Hamiltonians. And since my local Hamiltonian has some symmetries, right? So this is a symmetry operation on each physical Hilbert space, then it should be symmetric. And for this A tensor, A operator and B operator, I can push this physical symmetry, and some virtual space transformation will emerge, right? And so this becomes an important part, because I know that when I have this GTNO, this G operator, and this will becomes a virtual symmetry, right? So now I have a physical and a virtual relations in terms of this symmetry operation.
Sorry, how do you get this virtual?
Oh, okay, we just operate. So remember, I have these A's already. So I can just operate, say, I know that I have a symmetry group, right? So Z2, right? Then I can just apply my symmetry operation and see what comes out. Yeah, it's be easier when we see the examples. For example, here, I have an Ising model Z2 symmetry. So I can apply, so this, which is a sigma Z, a sigma X, sorry. Then the first set of my vector will be identity. So this will be 1 and minus 1. So these are the B's that I have. And written in terms of a matrix become a Pauli Z. And Heisenberg case becomes slightly more complicated, but then I have identity and with this associated rotation. So the good thing about this is that it doesn't really matter what kind of model you want to deal with, as long as you can write it in terms of two-side operator. So this is a cluster model, right? Sigma Z, sigma X, sigma Z. The three-side interaction. So I can decompose into two sides and just apply the symmetries, right? This model has a Z2 by Z2 symmetry. So one of the symmetry operator is you apply sigma X on even side, and the other one is on odd side. So I can do the same recipe and get all this, and then construct my G TNO. And I know exactly by this computation, I know that this symmetry of this physical symmetry becomes what virtual symmetry. Okay, So these are all mathematical construction. What's the physics behind this? The physics behind this is, remember, I want to construct this G as a representation of power of these local Hamiltonian terms. And so this term becomes, if I really expand it, so this is my IC model G, T, and O. So I multiply them, I get different strings. Okay. Since this case I have only two cases, so this one here I just represent sigma d, and 0 just identity. So when I expand this, these are the strings I'll have. Okay. So if you see here, these are the terms with only one sigma d pair at different sites. And these are the sigma d, two sigma d's, which are not disconnected. And there will be sigma d's are connected. And we assign each part of Hamilton, the operator some variational parameters. So here's the variational part comes in. By optimizing this, so I can take a wave function, apply this operator, I get a new wave function, but now with the variational parameters. But these variational parameters are very few. But I know that this wave function respects the original Hamiltonian symmetry. So by optimizing this C1, C2, these few parameters, I can adjust the weights of these different different strings, these different operator strings. And these strings actually, by doing this, I can get a very good wave function, a ground state wave function. Right, so these are technical usually I will not go through. And it's easy to just add on-site terms because there's a way to add on-site terms without increasing too much complexity. So let me just give you some examples. Okay. Sorry, this is just generic construction. So everything is actually included in this slide. If you have a two-side Hamiltonian or single-side Hamiltonian, you can always write in terms of this, and you assign a coefficient for each type of these vectors you have, and then we just use the recipe we give you and try to symmetrize it and get this operator, and then you know that the symmetry of the physical symmetry can be translated into some virtual symmetries, and also you can take a symmetric wave function and apply this and try to optimize it. And the hope is that the ground state wave function with proper optimization will describe the proper physics.
Oh yeah, I think I was. So how do you determine the number of C's of alpha?
Okay. So let's go to one. So here, okay. So the alpha is basically this is 0 and 1. Okay. So what I do is in this case, I have power 1, right? So I have a sigma d. If I square it, right? I square hij, then I have a identity. So I know that, and then I do it again. Third time, then I get the x sigma d. So I know that all I need is just identity, right? Then sigma d. So this is sort of like the closure condition. And I think that there's probably a mathematical rule to count this, because Heisenberg model I can have just 3. Right, and x, z, this is another. So the number of these vectors is actually limited because your algebra, your spin algebra is closed.
So it depends on SUN.
Yeah, basically.
And also the ideal Heisenberg.
Yes. So but this is something that we haven't figured out yet, but it's something related to the symmetry of your Hamiltonian and so also the internal algebra of your spin operator. But I think there must be some some formula I can compute. So I think that's a key thing because this dimension is actually small for spin 1/2 or spin 1. I mean, for higher spins, then you can see there's more.
But here you have like C2, right?
Yeah.
As well.
Yes.
C2 is basically you have identity and also C2 times identity,
Yes.
which.
So I can assign a parameter on each of these vectors, but there's overall constant I can absorb.
Sure.
So I assume this is 1. And this can be C1 and C3, right? But I know that I have this symmetry, inversion symmetry, so I just assign them to be the same. So this is where I can apply some space group symmetry in this case. Maybe I'll just skip some details. Okay, so here is a 1D case Heisenberg model. Okay, so we can compare with the exact result. Okay, so I can start with my wave function as a Marchand-Gauss state, which is at CO2 invariant. So I don't assume that any symmetry breaking or anything, right? And the ground state we know is a CO2 symmetric, and it's a gapless state, so it's an infinite correlation length. If you do a DMRG, because this log correction takes forever to convert. But as you can see, we can get a reasonable result with just 6 parameters to optimize. Okay, the correlation length is already very large. And to achieve this, the DMRG requires one dimension 100. Okay, and so another interesting thing is that I can start from a totally symmetric wave function. So it's a product state. I can start with a trivial. I can start with a trivial wave function, right? Trivial wave function. So basically, it's this the cast state. I didn't break the V2 symmetry, but I apply this GTO, and by optimizing these parameters, I can actually get a good result. Okay. So for example, I just apply this operator once to this product state wave function, then I can get so here is what we measure the virtual order parameter. So I compute this with applying this operator once, the sigma plot, and see if this is so this is a 0 means that I'm in a symmetry breaking state. Okay, so this is detects the symmetry breaking. Okay, and we can also use this method to study the transverse field cluster model. So this model is interesting because it's a topological transition from the trivial phase to a SPD phase. So to detect the SPD phase, we can just say, okay, we can detect this guy. Okay. So this guy, if this guy, if you apply this, I have a minus sign. So this is basically a projective representation. So I detect if this tensor is in the virtual space as a projective representation, and I can compute the difference between these two. If this is 0, then it's in the SPD phase. Yeah. So again, this is what we get. Okay. Although the real transition is at 1 is that solution, but this is just applied once, but we can really see this SPD to a trivial transition. So I'm running out of time. We can easily generate this, generalize this 2D and multi-side interaction. So we did a study of using this torical. You can add a torical, add a gain field. You also have a topological phase transition. And so with this construction, we can also see. So just focus on this blue curve. This is a virtual order parameter. So when it's 0, means that it's has a topological order, and when it's non-zero, means that the topological order is lost. So from this construction, and we don't really need to restrict the symmetry of our tensor, but these symmetries I can detect it afterwards and see if what kind of order exists. Okay. Let me conclude the summary. So I hope I convince you that we come up with some method that's actually simple. It's a standard recipe you can use, and it's quite generic, and you can get a very good result as far as parameters. And the good thing is that all this virtual symmetry will emerge. You just do the optimization, and then you say, okay, I want to see this stay at the D2 topological order. I can test them, and then I can see they emerge. So this is the method allows us to study symmetry breaking, SPT to trivial transition, topological order to trivial transition. Okay, so I think that there's a lot of extension one can do. I think it's a very powerful method. And then some outlooks. So this virtual order parameter is actually not well defined concept. It's not really universal. But recently there's a proposal one can define a slightly variational version of this. And you can even extract some critical exponents. But the interesting thing is to study physics, right? We want to see if we can apply this method to the SPT. Is there a way to study efficiency of stringness state? It's like a very interesting, even chiral spin liquid states. There's some other proposal recently. One thing we'll try to push is that there's a lot of speculation of the ground state of some p-type model, related models trying to describe the real p-type materials. Okay, for example, p-type Heisenberg K-gamma model. And so far, people can do, say, exact addition or DMRG or some tensor level type of calculations. But I think with this as a relatively simple construction, maybe we can push this further. With that, I thank you for your attention.
Thank you, Professor Kao, for this interesting presentation. We are open for questions. Perhaps if I can start. So what are typically system sizes that you can kind of achieve?
I forgot to mention, these are the infinite size algorithms. So we work in the thermodynamic limit. But the caveat is that so as you can see, what I show here, for example, this is the real transition. So you see that it's a finite size with quotation mark. So this is a so-called finite bound dimension. So I only apply my projection operator once. I can keep applying it so such that it gets to a closer and closer to a bound state. The price I pay is that it becomes computationally expensive.
So you can apply then some sort of like finite size scaling with
yes, but the finite bound dimension scaling is not as well defined as, because there's no RG except on the critical point you have a CFT you can sort of like define, but there's no such thing like the finite size scaling. You have an RG theory to back it up. Here, I haven't seen any development of that, except the critical point. You can have some other exponents.
Thank you.
A layman question, maybe this Kagome lattice simulation. How big was this simulation with this touch state?
Again, that's also infinite size, but the bound dimension is 24, 25.
25. How could you reach such a large? So you use a single layer?
You mean ours?
No. So
I think Kaohsiung had a very large bound dimension.
yes.
I think we did about, so this is the original tensor, it's not a cutoff.
And how did they contrast?
They have a single layer.
Single layer CTMR.
CTMR. So we also have a single layer.
So for SUN with larger n, then your kind of variation parameters will be bigger. So in that limit, can you claim that this variation is a better approach?
No, not that. I cannot. Actually, we're talking about maybe there's some way. I don't know if you know this. In the past, people do the SUN JK model. So if you choose the spatial representation, it becomes n copies of the same. Maybe that's something that we can try, but that's a very special representation of your sequence.
So I think closure condition is very important.
Yes.
So for example, if the spin like S equal to spin, then spin authority does not have the closure condition.
Yeah, even spin one, yes.
The spin on has, I checked. It's really flexible. It has the spin 2 case for 3/2. 3/2? I forgot. Anyway, so the closure condition is really important. If we don't have the closure conditions, then constructing the channel is kind of
You can do, but maybe
Yeah.
it becomes again computational, right? Not possible.
And also, it does not guarantee for multi-sites, like for the iron spin, the 3 spin interactions. In that case, we cannot guarantee this variation.
Yes. Yeah, that's very hard questions. But
cluster model has a 3-sided.
yes, but kind of treated because that's 1D.
Yeah.
And if you have say like triangle
right,
like this, then sure that's. You're asking very tough models to simulate.
Can I ask a question?
Please go ahead.
So if I have very complicated state, for example, type spin liquid in general model, do you think this variational tensor method, what is the name? So, sorry, variational tensor network operator method. Do you think it is how good, how useful this method would be?
So I think because actually what Kyung mentioned is important. So you need this. So to really construct this, I need this number of these vectors to be small. And this relies on when I take the power of these local Hamiltonians, how quick, like what's the minimum power that all the terms in this Hamiltonian will be generated. And if this is large, then this method is as bad as all other methods. But I think a good thing in terms of spin 1/2, there's only so many terms you can play with. So I think there's some potential, but I cannot guarantee. So one has to try.
Have you tried?
We are trying.
To find the variational method for the like a type spin liquid or any other color spin liquid basis.
Yes. So as I mentioned at the end, one thing we should definitely try to K gamma.
Mm.
And maybe if we were discussing that maybe this is a gamma model, if
Oh, yeah,
was the gamma model itself.
right.
Yeah.
The last one.
Yeah.
Okay.
I hope next year I can give you the definite answer.
Okay, do we have any other questions from the audience or from our Zoom participants? Seems not. So in this case, thank you again, Professor Kao. And with this we conclude our today's session.